Hello students, today I'm going to cover section 6.7, polygons in the coordinate plane. By the end of this lesson, you should be able to classify polygons in the coordinate plane. Today's key concept covers the formulas that are used in the coordinate plane and when to use them. All three of these formulas we've seen before: distance formula, midpoint formula, and slope formula. Today we'll be using them in a slightly different way in order to classify polygons in the coordinate plane using the properties that we've learned over the previous lessons. The first problem that we're going to look at today asks us to classify a triangle based on the lengths of its sides. We're given three vertices of a triangle and asked to describe the triangle as either scalene, isosceles, or equilateral. So first we plot our triangle on the coordinate plane. Once we have the triangle plotted, we should use distance formula to find the length of each side. Distance is determined by the square root of the difference of the y's squared plus the difference of the x's squared. So first we'll find the distance from A to B. The distance from A to B is determined by taking 4 minus 0 squared and adding to that 1 minus 0 squared and taking the square root of the result. 4 minus 0 squared is 4. So we have 4 squared plus 1 minus 0 is 1 squared. So we're taking the square root of 4 squared plus 1 squared. So we have the square root of 16 plus 1, which gives us the square root of 17. Next, we'll find the distance from B to C. The distance from B to C is given by 2 minus 4 squared plus 5 minus 1 squared. 2 minus 4 is negative 2, so we have negative 2 squared plus 5 minus 1 is 4, so we have 4 squared, and we're taking the square root of that. Negative 2 times negative 2 is 4, so we have 4 plus 16. And so the distance from B to C is the square root of 20. Since the distance from A to B is different than the distance from B to C, we can eliminate the possibility that this triangle is equilateral. Once we find the distance from A to C, we can confirm whether or not this triangle is isosceles or scalene. To find that distance, we take 2 minus 0 squared and add to that 5 minus 0 squared. So here we have the square root of 2 squared plus 5 squared. 2 squared is 4, so we have 4 plus 5 squared, which is 25. We have the square root of that. So this is the square root of 29. Here we have a triangle where all three sides are different. So this triangle is best classified as scalene. Our second question asks us to classify a parallelogram. So we're given a parallelogram with its 4 vertices and asked to determine specifically if it is a rectangle, and then furthermore if it's a square. Plotting parallelogram ABCD in the coordinate plane will give us a good indicator of what we're looking at. So our first objective is to determine if this parallelogram is a rectangle. In order to do that, thinking back to the properties of rectangles, we know that rectangles have to have 4 90-degree angles. We can confirm perpendicularity using slope. Slope is rise over run, so graphically we can see that this side of the parallelogram goes down 3 to the right 1, so it'll have a slope of negative 3. Continuing clockwise around the figure, this slope is positive 1 up, runs 3, so this has a slope of 1/3. This side of the figure goes down 3, right 1, so it has a slope of negative 3. And finally, the bottom of this figure goes up 1 over 3, so we have a slope of 1/3. By multiplying the slopes of consecutive sides, we can see negative 3 times 1/3 gives us a product of negative 1. All of the consecutive sides, when multiplied piecewise together, will give us this product. So we can see that consecutive sides of this parallelogram are perpendicular. Therefore, this parallelogram is in fact a rectangle. To determine if this parallelogram is a square, we have to do one of two things. We could either calculate the length of all four sides and confirm that they're all the same, or we could attempt to prove that this is a rhombus by showing that its diagonals are perpendicular to each other. In this case, if we want to check the distance on each side to prove that they're all equal, that would require 4 calculations. If we want to prove that the bisectors are perpendicular, that requires us to calculate the slope of each bisector, and then check their product to see if it's -1, thus proving that they're perpendicular. So in this case, the second option is better. If we were to calculate slope graphically, to get from here to its opposite vertice, we have to go down 2 to the right 4. So we have a slope of -2/4, which in turn reduces to -1/2. To calculate the other slope, we go from here to here. So we have a rise of 4 and a run of 2, which reduces to 2. If we take the product of -1/2 and 2, we see that it does in fact equal -1, thus making the bisectors meet perpendicularly, which then forces this parallelogram to be a square. So the answer to both questions, is this parallelogram a rectangle? Yes. And in fact, furthermore, this parallelogram is a square. Our final question asks us to classify a quadrilateral. We're given an isosceles trapezoid with its 4 vertices, and asked what special quadrilateral is formed by connecting the midpoints of that isosceles trapezoid. Again, we start by plotting the isosceles trapezoid that we're given. By using midpoint formula on A and B, we can determine the midpoint of that segment. So we have 0 plus 2/2, and we want the average of 0 and 4. So we have 2/2, which is 1, and 4/2, which is 2, so we have a midpoint of 1, 2. Continuing around the isosceles trapezoid, we can find the other 3 remaining midpoints. By connecting the 4 midpoints, we can see the special quadrilateral that we're supposed to be classifying. We can immediately rule out square and rectangle, since this figure does not have 90-degree angles. Having ruled out rectangle and square, we're left with the following options: kite, trapezoid, isosceles trapezoid, parallelogram, and rhombus. By checking to see how many opposite sides are parallel, we could eliminate one group altogether, either kite, trapezoid and isosceles trapezoid, or parallelogram and rhombus. So it seems to make sense to check the opposite sides to see how many sets are parallel. So in this case, we should look at slope. The slope of this line has a rise of 2, a run of 3, so we have a slope of 2/3. Checking its opposite side, it also has a rise of 2 and a run of 3, which means those opposite sides are in fact parallel. That eliminates kite. Checking the other set of opposite sides. This has a rise of -2 and a run of 3, and its opposite side also goes down 2 to the right 3, so also -2/3, meaning that that pair of opposite sides is also in fact parallel. This eliminates both trapezoid and isosceles trapezoid. We have confirmed that this is in fact a parallelogram by definition. However, it would be nice to be as specific as possible. To check to see if this is a rhombus, we could confirm that all 4 sides are congruent, that one diagonal bisects one pair of opposite angles, or to see that the diagonals meet perpendicularly. The final of those 3 options is probably the easiest in this case, since by drawing the diagonals we can see that one of them is horizontal and one is vertical. Since all horizontal lines and vertical lines meet perpendicularly, we can now confirm that this special quadrilateral formed is in fact a rhombus. That concludes section 6.7, polygons in the coordinate plane. You now have the ability to classify polygons in the coordinate plane.